A reaction wheel is a type of flywheel used primarily by spacecraft for attitude control without using fuel for rockets or other reaction devices. They are particularly useful when the spacecraft must be rotated by very small amounts, such as keeping a telescope pointed at a star. They may also reduce the mass fraction needed for fuel. This is accomplished by equipping the spacecraft with an electric motor attached to a flywheel which, when its rotation speed is changed, causes the spacecraft to begin to counter-rotate proportionately through conservation of angular momentum. Reaction wheels can only rotate a spacecraft around its center of mass. They are not capable of moving the spacecraft from one place to another. Reaction wheels work around a nominal zero rotation speed. However, external torques on the spacecraft may require a gradual buildup of reaction wheel rotation speed to maintain the spacecraft in a fixed orientation. A reaction wheel is sometimes operated as a momentum wheel, by operating it at a constant rotation speed, in order to imbue a satellite with a large amount of stored angular momentum. Doing so alters the spacecraft's rotational dynamics so that disturbance torques perpendicular to one axis of the satellite do not result directly in spacecraft angular motion about the same axis as the disturbance torque. Instead, they result in angular motion of that spacecraft axis about a perpendicular axis. This has the effect of tending to stabilize that spacecraft axis to point in a nearly fixed direction, allowing for a less complicated attitude control system. Satellites using this momentum bias stabilization approach include SISAT-1. By orienting the momentum wheel's axis to be parallel to the orbit normal vector, this satellite is in a pitch momentum bias configuration. A control moment gyroscope is a related but different type of attitude actuator, generally consisting of a momentum wheel mounted in a one-axis or two-axis gimbal. When mounted to a rigid spacecraft, applying a constant torque to the wheel using one of the gimbal motors causes the spacecraft to develop a constant angular velocity about a perpendicular axis, thus allowing control of the spacecraft's pointing direction. CMGs are generally able to produce larger sustained torques than RWs with less motor heating, and are preferentially used in larger and/or more agile spacecraft, including Skylab and the International Space Station. Implementation: reaction wheels are usually implemented as special electric motors, mounted along at least three directions, for example along the X, Y and Z axis provides no redundancy, while mounting four along tetrahedral axis provides redundancy. Changes in speed are controlled electronically by computer. The strength of the materials of a reaction wheel determine the speed at which the wheel would come apart, and therefore how much angular momentum it can store. Since the reaction wheel is a small fraction of the spacecraft's total mass, easily controlled temporary changes in its speed result in small changes in angle. The wheels therefore permit very precise changes in a spacecraft's attitude. For this reason, reaction wheels are often used to aim spacecraft carrying cameras or telescopes. Over time, reaction wheels may build up stored momentum that needs to be cancelled. Designers therefore supplement reaction wheel systems with other attitude control mechanisms. In the presence of a magnetic field, a spacecraft can employ manticores to transfer angular momentum to the Earth through its planetary magnetic field. In the absence of a magnetic field, the most efficient practice is to use either high-efficiency attitude jets such as ion thrusters, or small, lightweight solar sails placed in locations away from the spacecraft's center of mass, such as on solar cell arrays or projecting masts. Most spacecraft, however, also need fast pointing, and cannot afford the extra mass of three attitude control systems. Designers therefore usually use conventional monopropellant vernier engines for all these purposes. Failures and replacement: the failure of one or more reaction wheels can cause a spacecraft to lose its ability to maintain position and thus potentially cause a mission failure. 2 servicing missions to the Hubble Space Telescope have replaced a reaction wheel. In February 1997, the second servicing mission replaced one after electrical anomalies, rather than any mechanical problem. Study of the returned mechanism provided a rare opportunity to study equipment that had undergone long-term service in space, particularly for the effects of vacuum on lubricants. This was found to be in excellent condition. In 2002, servicing Mission 3B, astronauts from the Shuttle Columbia replaced another reaction wheel. Neither of these wheels had failed and Hubble was designed with 4 redundant wheels, and maintained pointing ability so long as 3 were functional. In 2004, during the mission of the Hayabusa spacecraft, an X-axis reaction wheel failed. The Y-axis wheel failed in 2005, causing the craft to rely on chemical thrusters to maintain attitude control. From July 2012 to May 11, 2013, 2 out of 4 reaction wheels in the Kepler telescope failed. This loss severely hampered Kepler-EURO's ability to maintain a precise enough orientation to continue its original mission. On August 15, 2013, engineers concluded that Kepler's reaction wheels cannot be recovered and that planet searching using the transit method could not continue. Although the failed reaction wheels still function, they are experiencing friction exceeding acceptable levels, and consequently hindering the ability of the telescope to properly orient itself. The Kepler telescope was returned to its point rest state, a stable configuration that uses small amounts of thruster fuel to compensate for the failed reaction wheels, while the Kepler team considered alternative uses for Kepler that do not require the extreme accuracy in its orientation as needed by the original mission. On May 16, 2014, NASA extended the Kepler mission to a new mission named K2, which uses Kepler differently, but allows it to continue searching for exoplanets. See also, Reaction Control System, Spacecraft Propulsion, ROSAT, a satellite lost when limitations in its control envelope were exceeded, UTC Aerospace Systems, the owner of Atharco Space Systems, Incorporated, which built the ill-fated reaction wheels for the Kepler, Dawn and Hayabusa spacecraft. References. External links: Sinclair, Doug. Grant, C. Cordell. Z. Robert E. Enabling Reaction Wheel Technology for High-Performance Nanosatellite Attitude Control. Reaction Wheel at Wolfram Research. June 2008. Markley, F. Landis. Reed G. Reynolds. Frank X. Liu. Kenneth L. Lipsock. Maximum Torque and Momentum Envelopes for Reaction Wheel Arrays.